Cool. Okay, welcome to, I believe this is lecture 16. Last class, we had this 2.5-hour class, so we did like a million things. We pretty much went over like a lot of homework, right? Tied up loose ends, and then we talked about the extreme value theorem, and we proved Fermat's theorem. Can I get some head nods? This is what happened? Yeah, all right, good. So, Brittany, today, or there was some homework due today, and the homework due today was 3 related rates problems, up a level of difficulty in my opinion, and bunch of problems where you had to find the maximum minimum, which was essentially just more derivative taking plus a little bit of algebra. Will, do you agree? Yeah. So let's go over, I don't know, do you want to go over these related rates problems? Like, I think we should do at least one of them, possibly two.
29.
We had to do two, which
29.
29 is at the swimming pool? No, which is 29?
29 is the,
Oh, 29 is the winch problem.
Okay.
Okay, we can do 29, and which other one would you recommend?
25.
25, the swimming pool? What was the third one?
31.
31 I thought was actually kind of chill, right?
Yeah.
Okay, I agree. Let's do these two. Alright, 25, this is a just great problem, swimming pool problem. Here is what the problem says. A swimming pool is 12 meters long, 6 meters wide, 1 meter deep at the shallow end, and 3 meters deep at the deep end. See figure. Water is being pumped into the pool at 1/4 of a cubic meter per minute, and there is 1 meter of water at the deep end at that moment. What percentage of the pool is filled? At what rate is the water level rising? Okay, so what we have is ultimately, can someone say it in a sort of precise mathematical language? What is the shape of this pool?
A trapezoidal prism.
It is a trapezoidal prism. That's exactly what it is. And so what we have is a trapezoid, and I produced some beautiful videos reminding you how to take the areas and volumes of these objects. So I showed that link to my friend, and he was like, "Dude, you need to learn how to draw dotted lines. What the hell's wrong with this?" But I still can't. Is that the dot? Is that where this dotted line is supposed to be?
No.
You
Supposed
want
to be on the
the
top right, probably.
You want?
Yeah, it's the one that you wouldn't be able to
Top
see.
right needs to
So
be
it's the
dotted
top
also.
right, like in the
And like
back.
you need to dot that
The
line.
one that you wouldn't be
Like,
able to see.
the one that you have dotted should be like half dotted.
Oh, this one.
No.
No.
That also should be dotted, right?
Yeah, it should be.
Yeah.
Right.
Nothing should be dotted. Water's transparent.
Yeah.
Ha ha. But the pool is transparent.
It's really scummy water.
Yeah,
This is the
yeah,
one
that
that's
should be
volume
dotted.
left.
What you just erased should be dotted.
Yeah, that.
And then the other part should be solid. Yeah.
Like that.
Yeah, and then that vertical
And then
line
that
over in the
part
upper
should
right
be
hand corner shall
solid. And
Wait,
then that
no,
should be
wait, why
dotted.
should that part be
The
solid?
other part is dotted should
It
be.
depends on how you look at it.
Oh,
Like it's like
okay,
an
okay,
opposite.
This is the front. This is the front.
Okay, then yeah, the top right, then that should be not
The
dotted.
left.
I see, yeah.
Wait,
yeah.
that
should be
That should be not
vertical would be
dotted.
dotted?
It doesn't really matter anymore because I can't do this. So
It's-
we're not
that
gonna.
should be solid.
Yeah, I was.
Okay, I need to take an art class. I promise to do that this summer, but this year you will suffer. All right. Moving on. This is precisely what we have. We have a trapezoidal prism, and this little guy up here is 1, and also the height of the trapezoidal prism is 6. This is all in meters. Okay. Beautiful. I love it. It's great. Is there another dimension that's relevant? Yes. This is 12. So, not to scale. Well, yeah, not to scale. Okay, so, then there's some water in the pool, and they tell you that the water is 1 foot deep. Okay, well that means,
1 meter.
crucially,
Meter.
well, 1 meter, sorry. So since the long base of the trapezoid is 3, since the deep end is 3 meters deep and the shallow end is 1 meter deep, if there is 1 meter of water, then it is like well within the this part of the pool, right? And so what we have is a kind of, you have to draw in the water in such a way that it also sort of forms a prism. There's like a prism of water here. How would you describe the shape of that prism of water?
Triangular.
It is a triangular prism, yeah. Good. And so, in fact, the first part of this question simply asks you a geometry question, which has nothing to do with calculus at all. What percent of the pool is filled? So this is just testing, hey man, can you actually just compute the volumes of trapezoidal prisms and triangular prisms? But it also gets you thinking about the relationships between the quantities in this problem. Can we do this? I think we can. What we need to therefore figure out is what is the volume of the triangular prism over the volume of the trapezoidal prism.
Follow.
All right. And can we do that? I think we can. The volume of this triangular prism, well, the volume of any prism is just the area of the base times the height. So, what are the dimensions of this triangular prism that I know of? Well, this is 1. Now I need to do a little bit of thinking. If this is 1, what's that? 4? No. It has to be 6. Why? Because of similar triangles. Yes. Crucially, and I guess it's a little bit hard to explain this if you didn't see it the first time, but if you sort of drop a perpendicular from like that point down, then what we have is a sort of situation in which the triangular portion of the trapezoidal prism, after the triangular portion is since that whole thing is 3 and that guy is 1, that's 2 and that's 12. If you didn't figure out this geometric relationship, then you pretty much couldn't do the problem at all. So since this triangle is a 2 by 12 triangle, when the triangle is only half as high, that has to be 6 by similar triangles. Is everyone cool? Raise your hand if you didn't see that relationship. Oh, good. Everyone saw it. Okay, good. And that's what this part A was all about. It was basically forcing you to see that relationship. So, thus, the volume of this triangular prism is 1/2 times the base, which is 1, times the height, which is 6. That's the area of the base, times the height of the entire prism itself, which is also 6. Over the volume of the trapezoidal prism is going to be the area of the trapezoid, and the area of the trapezoid is the average of the bases times the height of the trapezoid. So the average of the bases, 3 + 1 over 2, times the height of the trapezoid, which is 12, times the height of the prism, which is 6. Everyone following this?
Yeah.
I think lots of things cancel. Do we end up getting like 1/8?
Yeah.
6's cancel, that 6's cancel again, so it's 1/2 over 4 is 1/8. Alright, so 1/8 of the pool is filled. Yes?
I didn't really do any math for that one. I just looked at how many of those size triangles fit into it, and you can see that it's 8. Because
Okay, that's math.
Yeah, that
That's
makes sense.
Still math.
Yeah, because like you 2 rectangles, so that like the top, that's 4, and that top one.
So you just do like 1 and then do like another one and like another, so you just like 1,
Yeah.
2, 3, 4, 5, 6, 7, 8. Yeah, okay. Do you guys see what he's talking about? You just you kind of got lucky that the numbers worked out so nicely that you could just do that. But yeah, if you're a visual person, you can decompose this into like, that's one triangle, that's another one, that's another one, that's another one, another one. So yeah, 1, 2, 3, 4, 5, 6, like that, right? Yeah. Okay, cool. I like it. All right. Now the calculus. So read and understand the problem. Make a picture. Pick variables for the quantities which are changing. Okay, what changes as we fill up the pool with water?
The height of the water.
The height of the water is certainly changing. What else?
Volume.
The volume is changing. What else? Okay, maybe that's it. So let's let H be the height of the water and let V be the volume of water. So now I'm ready to state the information that I know. What I know is that the water is being filled at a rate of 1/4 of a cubic foot per minute. So meters. I don't know why I keep saying that. So dV dt is 1/4 of a cubic meter per minute. And what I want to know is something about the rate at which the water level is rising when the water level is 1. So I want to know what dH dt is when h equals 1. Okay. And I guess what's relevant is because they're asking about it when h is 1, I can actually sort of ignore the fact that the pool is a trapezoidal prism now. Because I am only asking about the rate at which it's changing over here near the, in the triangular section, which is kind of why it's complicated. Once the water level gets high enough, once the water level is like 2.5 feet high, then I claim by intuition that the rate at which the water level is rising is going to be constant, right? Because it's just ultimately, yeah, a trapezoid is really like a monster composed of like a triangle and a rectangle, except when it isn't. But most of the time, for nice trapezoids like this, it's just a triangle and a rectangle. So yeah. So we can really we can almost ignore that top meter of the pool because it's irrelevant for our purposes. All right, now comes the hard part, I guess, which is to construct a relationship between the variables. So what is the relationship between the volume and the height? Well, basically we just go right for the formula for the volume of the volume of the water. So what is the volume of the water? Well, I just need to calculate the volume of that triangular prism, and it's going to be the area of the base, which is 1/2 times h times, well now suddenly I realized, just like a minute ago, that I need to know what that thingy is, right? But hopefully your brain has been like greased up, and now you just know, duh, what is that?
6h.
That has to be 6h. Again, by that same similar triangles conversation we had, since that's 2 and that's 12, whatever this height is, that dimension of the triangle is always going to be 6 times as much. I feel like that is the one point in the problem that's hard. So this is going to be, so the area of that triangle is 1/2 h times 6h, and we multiply the area of that triangle by the height of the triangular prism, which is just another 6. All right, so now I have the relationship between the volume and the height. It is just 18h squared. And now the problem's just easy from here on out, right? Differentiate both sides with respect to t, and I get that dv dt is 36h back inside dh dt. And since I want dh dt, I'll solve for that. It's dv dt over, over 36h. And this is a quarter. So it's a quarter over 36h, so it ends up being 1 over 144h. That's dh dt in general. I want dh dt at h equals 1. So I just plug in 1, and the answer is 1 over 144, and the units are meters per minute.
It's a really small number.
It's a very small number. Yeah, well, the quarter of a meter per minute is not very fast. It's a big pool. It has to get spread out.
A long time though.
Okay. Question, how do we feel about this? Michelle? Cool? Cool. Okay, let's do 29, which I thought was conceptually easier, but algebraically harder. Maybe like strategically from a problem that we're doing. Raise your hand if you've got 29. Half the class or less? Brittany, 29? No? Okay. All right, what is going on? There is a winch. A winch at the top of a 12-meter building pulls a pipe of the same length to a vertical position as shown in the figure. Winch pulls in rope at a rate of negative 0.2 meters per second. Find the rate of vertical change and the rate of horizontal change. So you can either turn the camera or you can just pick it up and place it back down over there. So let's give it a nice shot of this whole thing. All right, so what's going on? Here is the building. And then there's like a dude up here, and he's pulling a pipe up. So imagine, here's the ground, and we have some long drain. So, might have made this picture too big. Just kidding, no such thing. The height of this building is 12, and we have a 12-foot long pipe, which we are trying to raise from the ground up to the building. Right, so how would you do this in practice? I guess you would take a long rope, go up to the top, then do something, throw down the rope. They would tie it to the rope to the end of the pipe, and you would just pull, right? And that would actually be pretty easy. That's pretty much like how you would do this. So that's what's happening, and we're checking into the situation like mid-winching. So we have a 12-foot long pipe, that look like it's going to work? We have a 12-foot long pipe, which eventually will match up exactly with the building. Okay. So, and they pretty much drew this picture for you, but if they didn't, it would have been a lot harder problem. They heavily suggested that you should call this point x comma y. Does everyone understand what's going on now? So now, okay, I read and understood the problem, drawn a picture, pick variables for the quantities which are changing. Well, what's changing as we pull this rope in? A lot of things, I guess. X, Y, and S. They also gave you this. They did a lot of the work for you, in my opinion, by drawing the picture and already picking the variables. That's the hard part, I think. So S is the length of the rope, and I do care about the rate at which this length of rope is changing. In fact, that's the only thing I have access to, right? I know how fast I'm pulling the rope because I can measure that directly. And if we call this point x comma y, well then what that really means is, I think it's important to draw in some of these quantities then, right? If that's point x comma y, it means that that's x, and that's y. So, and if that's y, and this whole thing was 12, then this little bit here is 12 minus y. So this is sort of my picture at the moment. It's looking pretty good. All right, and now what? Now I think we're ready. So okay, pick variables, read and understand the problem, draw a picture, pick variables for the quantities which are changing, some of which of those things I already did for you. Figure out what information they're requesting, what they know. What are we given? Which we know. We know the rate at which the rope is being pulled in. So what I know is that ds dt is -1/5 of a meter per second. And what I want is two things. I want to know basically the rate of vertical change and the rate of horizontal change at the end of the pipe when y equals 6. You got this problem? Is that what you're looking for? Okay, I'll go faster. I want to know what dx dt is at y equals 6. And I want to know what dy dt is at y equals 6. Everybody with me? So far not hard. I think this problem is just the doing it which is hard. Alright, so now I have to seek relationships between the variables. Well, what is one relationship between the variables?
X squared plus y squared equals 144.
Yeah, x squared. So I see two right triangles here, and I feel like I'm going to have to use both of them, right? This one says that x squared plus y squared is 144, so that's a relationship between x and y. But the only rate which I know of is ds dt, so I also need to find a relationship between x, y, and s. So what's the relationship between x, y, and s? Well, there's the other right triangle, right? So it's also true that x squared plus 12 minus y squared is s squared. And so somehow these two relationships are going to come into play. Well, there are lots of ways to do this, but to me the simplest thing to do is to get rid of one of the variables, at least for the moment, right? And what I'll do here, x squared is just 144 minus y squared. So I'm going to go in here and I'm just going to replace this x squared with 144 minus y squared. And then I think everything's just going to be beautiful now, right? This is, if I expand it, 144 minus 24y plus y squared equals s squared. I haven't done any calculus yet, just doing algebra. But I get a bunch of happy cancels. And this is like 288 minus 24y equals s squared. What this enables me to do is have a direct relationship between y and s. And once I have a relationship between y and s, now I can differentiate both sides with respect to t. Does this make sense? Okay, so this will be negative 24 dy dt equals 2s ds dt. And so, what is dy dt? Dy dt is just s ds dt over negative 12. And since I know ds dt to be negative 1/5, this works out to be s over 6d. Yeah. Cool. Alright, and now that's dy dt in general, so dy dt at y equals 6 is going to be 110. Is that what you guys got? Is that right? I feel like that's not right. Did I mess up
No,
somewhere?
that's S over, you're plugging in Y for S. You have S over 6, you're plugging in 6.
Oh, because the S is wrong. Yeah, sorry. It was right up till there, and then I did something really stupid. Right. I want to know what dy dt is when y is 6. So the answer is it's S over 60. Okay, so, all right, now I have to go back and do a whole nother kind of side problem, which is what is S when y is 6? Thank you, Griffin. So this is like 12. This is also 12. Well, when y is 6, it means I'm like at the midpoint, right? So that's 12. So that's kind of my situation, right? If x is 6, well then, no, sorry, if y is 6, then 12 minus y is also 6. So this is like a median, this is like the midpoint. And if it's also the perpendicular, then by geometry, this must actually just be an isosceles triangle. So I get that that's 12, and while I'm at it, I'll figure this out. This is 6 root 3. Does everybody follow that? That was just like a side geometry problem. It was necessary to determine at the particular time when y is 6, what is x and what is s. Okay, so now, since s, I just learned that s is 12 here, then this is 12 over 60. And so the answer is that dy dt is 1/5. A fifth of a meter per second. Alright, and now I'm half done. I also need to know what dx dt is. Well, what is dx dt? Well, now I don't have to come up with a relationship between x and s, because I can just use the relationship between x and y. This is a little bit subtle. So I'm going to take this equation, which is pretty simple, differentiate both sides, so that's 2x dx dt plus 2y dy dt equals 0. And the thing that's left for me to figure out is dx dt. So dx dt is just negative y dy dt over x. And what I really want is dx dt at y equals 6. So for that, I need to find these particular values. So this is going to be negative. Well, when y is 6, y is 6. What is dy dt when y is 6? Well, that's what I already calculated in the first half of the problem, right? I already know from the first half of the problem that dy dt is 1/5 when y is 6. Over what is x when y is 6? Now I look back at the geometry, and the answer is 6 root 3. So this whole thing becomes negative 1 over 5 root 3. Who is with me, basically? Good. All right, that's related rates. Guys, normally I just like keep assigning more problems, but I sort of don't feel like it. Do you feel like you've had enough of these now, or do you want to do a couple more? You think I should assign a couple more for homework? Maybe I'll just say they're optional with us. All right, there was another part of the homework which is far more relevant to what we're doing today. Let's spend a little bit of time on that. It's easier if you just pick up the whole camera and you just like move it. It's not really.
Yeah, I don't know where to move it though.
You don't know where to move it?
Yeah,
So you can make a decision.
Shake it a bunch.
Yeah. It'll be fun for the.
Oh, over here.
Okay.
Roller coaster.
No, please don't do that. So, how did these other problems go?
You're not in it, Sharon.
I just stay like that.
Wait,
Shall we
Sherry,
do
sit
like
up.
3 or which were
You're
were
good.
they?
You're not near the board.
5, 7, 15, 17, 19, 26, 27, 30.
Wait, that was too fast. 5, 7.
15, 17, 19, 26, 27, 33.
Okay,
Can you even see
and
that?
most of them were just most of them were just find the critical numbers or find the extrema, right? Let's do a couple of each. Oh, let's do 17. That's like a good problem. This trig is involved. Maybe we'll do 26 because it's also easy. We could do 19. Oh yeah. 19 gets a little ugly. And then, is that good? Or want me to do one more?
62.
Add your eraser.
It's kind of easy, but it's a little bit.
I don't feel like doing 62. How about 33? No, 27?
No.
27, 15? 15? Could do 15. Okay, so 15 just said find the critical numbers. Here was the function t root 4 minus t. So do you realize that this is this whole thing, and they say that t has to be less than 3. I don't know why they say that, they just do. So this whole problem is essentially just find the derivative and factor it correctly. Do you guys realize that? That's just everything, right? Can someone erase the front board while we do this? So how do we do this problem? We just do it. We write this in differentiation-friendly form, like that. Now we take the derivative. Griffin, stop talking. Derivative of this is, what? No, I didn't take the derivative yet. I just rewrote it. The derivative is the derivative of the first times the second. Plus the first times the derivative of the second, and that's 1/2 4 minus t to the negative 1/2. Back inside, careful. When you go back inside, the derivative of 4 minus t is negative 1. Okay, looking beautiful. Now, with my advanced skills that I have now, I recognize that the smart thing to do is to factor out a 4 minus t to the negative 1/2. And since I'm also experienced, I'm going to show off and take out a 1/2 at the same time, because that leaves everything not fraction. So when I do that, well, since I took out a 1/2, that means 2 is going to appear here suddenly. And 4 minus t to the negative 1/2 times 4 minus t to the what will give me 4 minus t to the 1/2. That exponent has to be 1, right?
Yeah.
So this is like advanced algebra moves. And then this becomes just minus t. So this is just a really, really fast way to factor a derivative, which is the result of a product rule. So I can now rewrite this as, what is that, 8 minus 2t minus another t? So that's 8 minus 3t. 8 minus 3t over 2 root 4 minus t. And maybe I'll even do one more step, which is to factor out a negative 3. This is some beautiful algebra going on here. And this becomes now t minus 8/3. Why I like this is because now it's just really, really easy. You need to get into the habit of doing this. Take the derivative and then just put in the effort to just factor it in a beautiful way, such that now I can just look at this immediately and tell you where the critical values are. And where are the critical values? It's wherever the derivative is 0 or does not exist. Well, the derivative is going to not exist at 4, but for some reason they want me to only consider numbers less than 3. So when is the derivative going to be 0? At 8/3. So the only critical value is 8/3. Cool? Okay. 17 is
Michelle, you're good.
conceptually the same, but now trig skills are involved. What's up? Are we good? Trig skills are involved. So again, it's just take the derivative. So the derivative of sine squared is 2 sine back inside cosine plus the derivative of cosine is negative sine. Okay, excellent. Let's again factor. If I factor out sine x, then I'm left with 2 cosine x minus 1. And figuring out when this is 0 is pretty much easy. It's going to be, this derivative is going to be 0 whenever sine is 0 or whenever cosine x is 1/2. And they specifically wanted me to do this on the interval from 0 to 2 pi. And on the interval, is that what they said? 0 to 2 pi like that, right? Or no? For some reason they said open 0 to 2 pi. So in that case, when it's sine 0, sine is going to be 0 at pi. And cosine is going to be 1/2 at pi over 3 and 5 pi over 3. So those are the 3 numbers which make the derivative 0, and the derivative is never undefined, so we're just good. All right. 19 is another problem that is a little bit weird. The function is, sorry. The function is x squared log base 2 of x squared plus 1. Okay, so let's differentiate and find the critical values. Well, the derivative of this, I guess I just have to use the product rule. The product rule says derivative of the first times the second plus the first times the derivative of the second. What is the derivative of log base 2 of x squared plus 1? Well, the derivative of log base 2 of something is 1 over ln 2 times 1 over the something back inside for the derivative of the something. All right, so now let me attempt to factor intelligently. If I factor, I guess I can take out a 2x, right? So if I take out a 2x, then I'm left with log base 2 of x squared plus 1 plus x, well, 1 over ln 2 times x squared over x squared plus 1. Alright, this is just disgusting. However, with advanced knowledge about all these functions, I can make a startling conclusion, which is,
That's always
explain,
It's always positive.
explain.
Because
x squared over x squared plus 1 is always positive, because like when you square stuff, it becomes positive. And then
Yeah, Richard, can I get a red
if you
marker?
graph like log functions, they're always positive, because they're just like not always.
They're not always positive.
Well, like, oh, wait, because x.
It's a little bit subtle.
Oh, wait, actually. Well, ln, 1 over ln 2 is definitely always positive. It's a constant.
Okay, this is just a number. I mean, ln 2 is just a number. And ln 2 is going to be positive, because natural log is positive after 1. I mean, that's sort of what's crucial. All log functions go through the magic point, and they're positive after 1. Okay, well, what can I say about x squared plus 1?
greater than or equal to 1.
Yeah, x squared plus 1 is always bigger than 1, so the log base 2 of x squared plus 1 is guaranteed to be positive. This is someone following this? That's guaranteed to be positive. That's just a positive number. And these numbers are also all positive. So everything in this brackets is positive, and thus there are going to be no critical points arising from that factor. And thus I can claim, I can say that the only critical value is this one. Okay.
Someone needs to fill it out.
Okay.
I can wait, yeah.
Okay. Oh, you need me to do it like now?
Yeah.
Okay. So this is critical. So the critical value is when x is 0. Okay. Someone do that was 19. Someone do 26.